Mm.
So how is potential energy neglected actually?
Kinetic energy is also neglected. It it is an adiabatic device, so Q is
Mm.
also neglected.
Okay.
Mm,
Sir, almost everything is
mm,
neglected,
let's see.
Mr. Then
Uh-huh.
what?
Now, finally, what you are getting, tell me, which equation, most probably, which equation you are going to get in turbine, steady flow energy equation?
So that W is equal to M into H2 minus H1, where
Good.
H1 is enthalpy at inlet and
Uh,
H2 is enthalpy at outlet.
correct. Okay. Like that, you have to analyze the device. Okay. So whenever they give the device, first you have to analyze. First, you have to write the steady flow energy equation and what parameters you are going to neglect in that particular equation. For example, you take turbine. Okay. So as we know, turbine is a power generating device. So that work done is most important. So that first you have to consider work done in that one. Okay. Next, coming to the your velocity, the velocity terms are almost same. Okay, at the inlet and outlet. Okay, it is approximately same, and we are neglecting that one also, and we are neglecting Z1. Z1 means your the potential term, and that is Z1G.
Sir,
You are,
shouldn't
tell me.
suppose,
Hmm.
sir, in a hydroelectric dam there are
Hmm.
turbines, right? So if you let water fall
Hmm.
from a height on the turbines, there are
Yeah.
changes in potential energy, kinetic
Yeah.
energy as well.
Mhm. No,
With that
actually,
logic,
correct.
then
Okay, whenever you are taking the within the turbine itself, datum line. So in that case, Z1 and Z2. Suppose if you are considering different head, suppose and dam level and those things, in that case you have to consider Z1 and Z2. Okay, so whenever you are considering the turbine itself as a system, and we are considering the datum line passing through the center line, in that case Z1 and Z2 are same. Okay.
what about the kinetic energy, sir? When
And
water is coming at a high speed into the
it,
turbine, it's
mm,
going to make the turbine rotate and
mm,
it's going to give up some of its energy, right? And that comes
mm,
from the kinetic
mm.
energy, right?
Mhm,
So
kinetic
how can
energy.
you
Mm.
how can you assume that the velocity of the the liquid or the fluid will be the same both before it strikes the turbine and after it strikes the turbine?
The
There
al-
should be a great variation, right?
Mm, correct. So whenever considering especially velocity, it is approximately so equal. Okay, so velocity whatever you are entering at the inlet, because it's not so much difference at the outlet. Okay. So for when you consider in case of nozzle, okay, for example, the velocity of the fluid entering the nozzle at around 4 meter per second and leaving around 400 meter per second. In that case, the difference is too high. In that case, we are going to consider the velocity. Okay. In case of turbine, almost is velocity is almost equal. Okay. Whatever the velocity entering at the inlet is almost leaves at the same velocity. Okay. It means the proportion is less as compared to other devices. Whenever you are concentrating more on the velocity, in that case, we are going to consider the velocity term. Okay, especially in case of a nozzle. Okay, whatever you asked, it is exactly right. But the difference is not so high. We're not going to consider that one. Okay, and almost for example, in case of nozzle, the velocity enters to the nozzle. Almost we are going to neglect that one. Okay, we are not going to consider that V1 in the final equation only because the proportionate is too high. But in case of this one, in case of turbine, suppose one is 200 and another one is 250 meter per second. In that case, we are not going to consider that velocity too much. Okay, we are neglecting that one. Okay, whenever the proportion is
Sir,
too high,
yeah.
in that case, we are
Uh,
going to consider. Tell me.
so in the case of nozzle, we can ignore the entering velocity, right? Because the
Uh-huh.
exit velocity is very high.
Correct.
Okay. So as long like what should be the minimum say difference, sir? So like
Um,
when this can be applied? Like
mm.
minimum how much?
No, okay, for example, that's why is so as we are going to see in the numerical problems and those things, the velocity enters the nozzle at 4 meter per second, and at the outlet we are getting 600, 650, 700 meter per second like that. Okay,
Okay.
yeah, in that case, almost we are neglecting. Okay, suppose you want to consider that one only. Okay, that's a little bit
Sir,
variation. Mm,
sir, if like a liquid or
mm,
any fluid is
mm,
exiting a
mm,
nozzle, suppose
mm, mm,
it is exiting the nozzle at say 700 meter per second.
okay. Mm.
So that's much faster than the speed of sound, right? So will it like cause a sonic boom?
Sonic boom. So, what is the range of the sonic velocity? Can you tell me?
So
Do you know?
343 meter per second, sir, in air.
Mm-hmm.
When as soon as a object crosses 343 meter per second at 20 degrees Celsius in air, like
Mm-hmm.
especially aircraft and bullets and all that, they
Mm-hmm.
cause the shock waves in front of them, and those shock waves propagate in the conical fashion and they cause sonic boom. This is what we have studied in
Mm-hmm.
engineering physics in second semester. So
Correct.
my question was, they use this water cutting jets, right?
Mm-hmm.
In like in industry when they're cutting tough metals, often they
Mm-hmm.
use water cutting jets. So
Mm-hmm.
I was reading that the speed is, as you said, they use nozzles, so that 700, 800 meter per second. So I was
Mm-hmm.
wondering, that is, does that not cause a sonic boom? If because it's still the same condition. Right? But when I saw a few videos of it working, there was no such thing, sir. No sonic boom. People were using it like a regular device, so it was very, different. So I was wondering, how is it possible?
Nozzle are used in aircrafts? No, I don't think so.
Sir?
Nozzles are
No,
not
no, I'm
used
not
in
talking about aircraft, sir. I'm talking about water cutting jet.
water cutting jet. Yeah.
Yeah, when water cutting jet is used to cut the metal,
Mm. Mm.
they, the water is coming out at a very high velocity, like 767 or 800 meter per second.
Mm.
So if any object in air, if it goes more than speed of sound in air, the
Mm.
pressure waves it creates in front of it cannot move away as quickly, right? Because the pressure waves can move only at the speed of sound, but the
Mm.
object is moving much faster. So
Mm.
all the pressure waves, they come together at the, front of the
Mm.
object. They get like squeezed together, and they, you know
Mm.
go out of that place in a conical fashion, like a explosion kind of thing. So that's the boom sound.
Mm.
So this water jet, when I saw, even though it was traveling at such a high speed, which uses that nozzle principle only, even though it was traveling at that high speed, it did not cause sonic booms. So I was wondering, how is it possible?
Okay, I'll go through and I'll let you know. Okay, that I'll go through.
Yes, sir.
I'll let you know. Okay, correctly.
Yeah.
So I'll go through and I'll tell you clearly what is
Yeah.
the.
Also, can you please find out whether,
Mm. Mm.
if air travels at such velocities,
Mm.
whether it will cause a sonic boom?
Okay.
Like in detail,
I'll
can
go.
you?
I'll go through and clarify. Okay.
Yeah. Thank you, sir. Thank you.
Uh, you're discussing with the steady flow energy equation. Okay, already I derived. Okay, but this is as important. That's why I'm doing once again this derivation of steady flow energy equation. Okay. Before that, whenever they ask to derive the steady flow energy equation, you have to write this diagram. Okay, remember this diagram. These are the parameters involved in the steady flow energy equation. First, you have to draw the steady flow device, and then it is bounded by a control surface. Okay, do anybody know what you mean by control volume and control surface? Okay. What is the meaning of control volume? What is the meaning of control volume? Anybody? This is one of the important concept. Okay, you studied in first module only. What is the meaning of control volume and control surface?
So control volume is the volume
Hmm.
of a space in which the characteristics, I mean the properties of the constituents in that region of space remain constant with respect to time.
My question is whether it is related to open system or closed system.
So control volume
So it
is
is open
open,
system, open
yes.
system.
Hmm.
But even though it is open, it is going to you know maintain a sort of equilibrium.
Hmm. We studied that closed system, open system, and isolated system. In case of closed system, the mass of the system remains constant. Okay, the only energy transfer takes place between system and surroundings. On the other hand, in case of open system, both mass transfer and energy transfer takes place between the system and surroundings. And in case of open system, so we are having a term called as control volume. Okay, in case of open system, we can consider the entire portion of the system as a boundary. For example, suppose you consider a gas enclosed in a cylinder. Okay, the inside boundary we can consider the entire the system. Okay, on the other hand, we can consider certain part of that in the part as a volume for analysis as a thermodynamic system. Means there will be a change in boundary. According to our the study. Okay, so that is called as control volume. Control volume means we can concentrate the entirely on the entire system, or we can consider certain part of the thermodynamic system. Okay, so this is mainly related to the open system, the control volume, and the surface which is bounded by a control volume is called as the control surface. Okay, what you are seeing, it is a related to open system. You remember, it's not closed system. Okay, so this is steady flow device. We have, it may be anything. Steady flow device means it may be a boiler, it may be a condenser, it may be a turbine, compressor, or it may be a nozzle, whatever it is. Okay, it is a steady flow. Means steady flow means the thermodynamic properties will not vary with respect to time. Okay, the thermodynamic properties are invariant with respect to time. That is a steady flow device. Here we are having the fluid inlet. You see that it is a section 1, the fluid inlet, and we are having the bottom line as the datum line. Okay, so whenever you consider the datum line is we are taking from the bottom of the device. Okay, it's a reference line. From that reference lines, we are going to take the where the flow takes place and where the flow inlet takes place and the where the fluid outlet takes place. Okay, this is the datum line. With reference to that line, so we are going to know the datum Z1 or Z2. Okay, suppose when you consider the in between, as we studied in turbine, that Z1 equals to Z2 means we are assuming that the datum line passing through the center of the device. Okay, here we consider the datum line at the bottom of the device. So obviously Z1 and Z2 are different. Okay, so here it is a Z1 and here it is a Z2, and here Q1 is the heat inlet to the system, and W is the work output from the system, and whatever the volume is, it is shown a volume. So the volume within the control surface, and this is the fluid outlet, and this is the datum line. Okay, so whenever they ask to derive the steady flow energy equation, first step is you have to draw the correct diagram. Okay, showing all the details. Okay, then after that you have to show what are the parameters involved in the thing. Okay, A1 and A2 are the cross sectional area at inlet and outlet. Okay, capital A1, A2, the inlet area. Okay, and then we are having a W1, W2, small W1, small W2 is the mass flow rate at inlet and outlet. Okay, it is also represented by M1 and M2. Okay, next we are having a small V1, V2. Small V1, V2 is our specific volume at inlet and outlet, and then capital V1, capital V2. Okay, that is the velocity of the fluid at inlet and outlet. Okay, first term is A1, A2. Capital A1, A2 is the cross sectional area at inlet and outlet. Next, we are having a small W1, W2 or M1, M2, that is the mass flow rate at inlet and outlet. Small V1, small V2 is a specific volume at inlet and outlet. Next, V1 and V2, that is the velocity of the fluid flow at inlet and outlet. Next, we are having the terms P1 and P2. P1 and P2 are the pressures at inlet and outlet. Okay, next we are having Z1, Z2, elevation above the datum line. And then apart from this one, we are having Q1 and W. Q and W are uh, the heat input to the system, and W is the work output from the system. As we know that this first law of thermodynamics mainly deals with the law of conservation of energy. The energy is neither created nor destroyed, but it can be transferred from one form to another form. So Q is taken into the system and W is taken out of the system. Okay, and whenever you are going to express in terms of rate, then we are going to write as dq by dt. dq by dt is nothing but the net rate of heat transfer through the control surface, and it is expressed in terms of joules per second. And whenever you are going to express W in terms of rate, we are going to write it as dW by dt. dW by dt is the net rate of work transfer through the control surface. So these are the parameters involved in the steady flow energy equation. Okay, so there are two things. One is the mass balance. Okay, so as I said, there are two things. One is the mass balance, and one is the energy balance. Anybody know what is the mass balance? How we are going to write the equation? Mass balance. So,
Sir, W1 is equal to W2.
correct. W1 equals to W2. W1 is mass flow rate at inlet, and W2 is mass flow rate at outlet. And what is the formula? As I say, do you remember?
Sir, A1 V1 by small
Hmm.
V1 is equal to A2 V2 by small V.
Okay. What is that meaning of small v1 and capital V1?
So small V1 is the specific volume of it and capital V.
Hmm. Okay. Here, where so whenever they ask, you have to first write down the mass balance and energy balance, because in case of the open system, both mass and volume, sorry, mass and energy crosses the boundary of the system. Hence, you have to consider both mass balance and energy balance. First one is the mass balance. You have to write by the conservation of mass. If there is no accumulation of the mass within the control volume, then the mass flow rate occurring at the inlet is equals to the mass flow rate crossing the boundary. Okay, so W1 equals to W2. W1 is here the mass flow rate at inlet equals to W2, that is mass flow rate at outlet. And remember the formula, whenever they ask the problems to find out the mass flow rate, you have to use this formula, capital A1 V1 divided by small v1 equals to capital A2 V2 divided by small v2, where capital A1 and A2 are the cross-sectional area of the fluid entering and leaving the system. Small v1 and small v2 are specific volume. The unit of specific volume is meter cube per kg, and V1 and V2, capital V1 and capital V2 are the velocity of the fluid entering and leaving the control surface, and it is going to express in terms of meter per second. Okay. So our unit of fluid flow rate is kg per second. So A1 capital V1 divided by small v1, how will get, means A1 is meter square into meter per second divided by meter cube per second. So meter cube gets cancelled. You will get finally kg per second. That is the fluid flow rate entering and leaving the control volume. Okay. Next, you have to write uh, the energy balance. Then you have to write the principle also. Okay, how we are going to write the principle means if there is no accumulation of energy, then by the law of conservation of the energy, the total rate flow of all energy stream entering the control volume must be equals to the total rate flow of all the energy streams leaving the control volume. So this statement you have to write for the energy balance. Okay. So you have to write the law of conservation of energy. So statement is by the law of conservation of energy, the total rate flow of all the energy streams. Okay, what we are dealing with now is only one single stream, but in case of steady flow device, it may be more than one inlet and more than one outlet. Okay, so but we are dealing with here the only one inlet and outlet, but there may be more than one inlet and outlet also. So you have to write in a statement like that. The total rate of flow of all energy streams entering the control volume must be equals to the total rate of flow of all the energy streams leaving the control volume. Okay. So as I said, okay, so this one is mass flow rate of internal energy plus potential energy plus kinetic energy plus flow work equals to the whatever the energy terms, that is it includes internal energy, potential energy plus kinetic energy plus flow work add to plus work done. Okay, so these are the energy streams entering at the inlet. Okay, so you have to consider flow work into account, the all energy terms into account, and whatever the Q it enters into the system. This is what the all the energy streams entering the control volume. That is internal energy, potential energy, kinetic energy, flow work from 1 to 2. It is flow work at inlet plus Q is uh, the rate of heat transfer equals to the mass into the internal energy plus potential energy plus kinetic energy at section 2 or at point 2 plus flow work at point 2 plus the work done. Okay, where Q dot, you see, remember sometimes we are going to represent it as dot. M dot means mass flow rate, Q dot is our heat flow rate, and W is the work done in terms of joules per second. Okay. So Q dot is dq by dt. Similarly, W dot is dw by dt. Remember, dot indicates the rate. Okay. So sometimes in most of the books they used to refer like this dot. Next, we have to write in the statement m into u1 plus gz1 plus v1 square by 2. Okay, so this is the internal energy at point 1 is u1 plus potential energy is gz1 plus kinetic energy is v1 square by 2 plus m into flow work is p1 v1. Okay, at point 1 plus q dot as it is m into u2 plus gz2 plus v2 square divided by 2. Okay, now I'm doing only the final equation. I already derived the derivation. Just you go through the derivation. Okay, so I am highlighting the things how we are going to do. Okay, this is the final equation. Actually, is the derivation is different. So we are having a lot of terms involved in that derivation. Okay. Next, U2 plus potential energy is Gz2 plus kinetic energy is V2 square by 2 plus M into P2 V2 plus W. So these are the three things involved. Okay. Next, now for the next step, you have to take that P1 V1 inside this term. Okay, already we are having U1 plus Gz1 plus V1 square by 2. You have to take P1 V1 inside the bracket. So you get M into U1 plus P1 V1 plus Gz1 plus V1 square by 2 plus q dot equals to m into u2 plus p2 v2 plus gz2 plus v2 square by 2 plus w. Now you tell me what are the things you know about internal energy and entropy? Anybody? You studied first law of thermodynamics and second law of thermodynamics. How we are going to differentiate between these two terms? Anybody? How to make difference between these two? What is the difference between your internal energy and entropy? I'll tell the internal energy is neither heat energy nor the work energy, but it is the energy associated with the system. Internal energy is always function of temperature, and it is given by the formula delta U equals to mCV into delta T. Whatever process it may be, you have to take this equation as delta U equals to mCV into delta T. So on the other hand, entropy, the second law of thermodynamics gives a new definition called as the entropy. So entropy is given by dq by t. Okay, it is mainly associated with the heat transfer. As the heat added to the system, the entropy of the system increases. As you take the heat from the system, the entropy of the system decreases. Okay, and we studied dq by t equals to 0 for reversible flow. Dq by t is the less than 0 for irreversible flow. If dq by t is greater than 0, then that cycle is not possible. Okay, so these are the differences between internal energy and the entropy. Okay, and internal energy is also given by mCV into delta T, and one more formula you should remember, that is the change in enthalpy. Change in enthalpy is always given by mCp into delta T. Whatever process it may be, isothermal, polytropic, or adiabatic, these two formulas you should remember. Okay, and here m into u1 plus p1 v1 plus gz1 plus v1 square by 2 plus q equals to m2 u2 plus p2 v2 plus gz2 plus v2 square by 2 plus w. Okay, so since u1 plus p1 is your h1, okay, so you put m into h1 plus gz1 plus v1 square by 2 plus q m into h2 plus gz2 plus v2 square by 2 plus w. Okay, this equation is called a steady flow energy equation. While solving the problem, you should remember this equation, that is m into h1 plus gz1 plus v1 square by 2 plus q equals to m into h2 plus gz2 plus v2 square divided by 2 plus w. Okay, if the mass of the fluid is taken as unity, okay, then steady flow energy equation reduces to, if it is 1 kg per second, then h1 plus gz1 plus v1 square by 2 plus q1 to 2. As I said, q and w you have to represent by symbol like this, q1 to 2, because it is a path function. Okay, uh, equals to h2. H2 is the point function. So all thermodynamic properties are point functions. Our enthalpy, entropy, internal energy, temperature, pressure, volume, etc. are the point functions, and also thermodynamic properties. And Q and W are path functions. H2 plus GZ2 plus V2 squared divided by 2 plus W. Okay, all the terms in this one are in unit mass flow of fluid joules per kg. Just a minute, guys. 2 minutes. Guys, tell me, is it visible for you? Screen is visible. Am I audible, students?
Yes.
Okay. I'm sharing the screen. Please tell me whether it is visible or not. Tell me, is it visible?
No, sir.
No.
Now it is visible.
Okay, okay, okay. Okay, I am doing one problem on study for energy equation. Okay, so such kind of problem they will ask. Okay, you see, first I am reading the heading. Air flows steadily at the rate of 0.5 kilojoules per second through an air compressor, entering at 7 meter per second velocity, 100 kilopascal pressure, and 0.95 meter cube per kg volume, and leaving at 5 meter per second, 700 kilopascal, and 0.19 meter cube per kg. They are given mass flow rate as 0.5, the velocity is 7 meter per second, that one capital V1, 100 kilopascal pressure, P1 is 100 kPa, and small V1 is 0.95 meter cube per kg, and leaving at 5 meter per second, means it is V2 is 5 meter per second, P2 is 700 kPa, and small V2 is 0.19 meter cube per kg. And the given one more condition is that the internal energy of the air living is 90 kilojoules per kg greater than that of air entering. Can you tell me what is the meaning of this one? Internal energy of air leaving the system is 90 kilojoules per kg greater than that of air entering. What is the meaning? Means U2 is U1 plus 90. Okay, that is the meaning of the statement. So U2 final internal energy equals to the initial internal energy U1 plus 90 kilojoules greater than that of system, because internal energy of the system increases in this system. Next, the cooling water in the compressor jacket absorbs the heat from the air at the rate of 58 kilowatt. Okay, so cooling water in the compressor jacket absorbs the heat. Okay, absorbs the heat from the air at the rate of 58 kilowatts. 58 kilowatts means 58 kilojoules per second. So we have to calculate the rate of shaft work input to the air in kilowatts. That is W. We have to calculate. Okay. Find the ratio of inlet pipe diameter to outlet pipe diameter. Okay. So here, just you have to write the simple diagram. That is a flow diagram for air compressor. The V1 is 7 meter per second, V1 is 100 kilopascal, and V1 is 0.95 meter cube per kg. These are the conditions at inlet. You show inlet 1 and inlet outlet is V2 is 5 meter per second, V2 is 700 kPa, and V2 is 0.19 meter cube per kg. And here Q is minus 58 kilowatt. Okay, so in case of air compressor, that as I said, there will be heat absorption. Absorption means that is from the device to the compressor, means it is a negative. We have to take minus 58 kilowatts. Okay, and here we have to write the steady flow energy equation. So this is important. W into U1 plus P1 V1 plus V1 square by 2 plus Z1G plus dQ by T. All the terms are in rate basis. That is dQ by dt equals to W into U2 plus P2 V2 plus V2 square by 2 plus Z2G plus dWx divided by dt. Okay. So our aim is to find out the rate of work done in terms of kilowatts. Okay, so we have to find out dwx by dts minus w into, you can write w, you take common in the bracket, we can write u2 minus u1, p2 v2 minus p1 v1. It is a flow work plus v2 square by 2 minus v1 square by 2 plus z2 minus z1g into dq by dt. So okay, actually minus, you have to write minus, so minus symbol is not there. So whenever you shift the term towards this one, it becomes minus, so it's a minus. So minus 0.5, so minus is there, 0.5 kilogram per second, it's our mass flow rate. 90 u u2 is u1 plus 90, so u2 minus u1 is nothing but 90 only. Okay. So u1 plus 90 minus u1 is nothing but you get 90 only, u2 minus u1, because u2 is u1 plus 90, so u2 minus u1 is nothing but 90 plus p2 v2, p2 is 7, here 7 meter per second into v2, small v2, small v2 is 0.19 minus p1 is 1. Okay. So here we can write directly 700 into 0.9 because they have taken 100 outside. It's not required. So you can take 700 into 0.19 minus 100 into 0.95 directly. Okay. So we have to express in kilo units. You can write 700 into 0.19 minus 100 into 0.95 directly. Plus here 5 square minus 7 square divided by 2 into 10 to the power of minus 3. Okay. Can you anybody tell why this is minus 3, 10 to the power of minus 3 in velocity? As I said, the conversion is most important here. So why you are putting minus 3 here? Suppose if you are not putting minus 3, 10 to the power of minus 3, your entire problem becomes wrong here. Okay. What is the necessity of putting 10 to the power of minus 3? Anybody analyze and tell me? Here, all the units are in kilo. Okay, first one is kilogram. Okay, second one is in kilojoules per kg, and third one is in also kilogram. Okay, but this fourth unit velocity they are given in meter per second. So we have to convert the meter into the kilo units. That's why the meter to kilometer, that is 10 to the power of minus 3. That's why this is a one factor is the most important. Suppose you are not writing this to a turn, so your entire problem becomes wrong. That's why be careful in conversion of the unit, especially in steady flow energy equation. So 5 square minus 7 square into 10 to the power of minus 3. Otherwise, what you can do, this one 5 meter into kilo units you can convert. Okay, 5 into 10 to the power of minus 3 whole square minus of 7 into 10 to the power of minus 3 square. Like that you can do it. Okay, divided by 2. So here this term is most important, velocity. Okay, because all the terms are already in kilo. So fourth term you have to express in kilo. That is 5 into 10 to the power of minus 3 square minus of 7 into 10 to the power of minus 3 square divided by 2. Uh, Minus of 58. Okay, that is minus of q is nothing but minus of 58. Then after solving this one, we are getting the answer as minus 122 kilowatts. That is the rate of work input is 122 kilowatts. This is how to find out the work. Okay, most of the problem will ask what is the work done, what is the heat transfer, what is the change in internal energy. In this problem, they ask the rate of work output. That is, so how much amount of the work we are going to obtain in an air compressor. That is, see, we are getting minus answer. Why minus? Minus means you see the device. Device is air compressor. Air compressor is work absorbing device. So obviously you'll get the answer in negative only. For turbine, you'll get the work in positive magnitude. Okay, and for blower, you are getting the answer in negative. And air compressor, blower, pump, all the devices are the work absorbing devices. So you're getting the answer in negative magnitude. Okay. Next part, you have to calculate the what is the ratio of diameter at inlet and outlet. So see, we are going to apply the mass balance equation here. Okay, the mass balance equation. According to the mass balance equation, uh, mass flow rate at inlet equals to the mass flow rate at outlet. So A1 V1 divided by small v1 equals to A2 V2 divided by small v2. So this is the mass balance equation. So and from this one you have to find out the ratio at inlet and outlet, that is A1 by A2 equals to small v1 by v2 into v2 divided by v1. So just you substitute the values given in the problem. Small v1 is 95, small v2, that is specific volume at outlet is 0.19 into the velocity at outlet is 5 and the velocity at inlet is 7. So after solving this one, we are getting 3.57. Okay. So we know that A1 equals to pi by 4 d1 square and divided by pi by 4 d2 square. Our aim is to find out the ratio of diameter. But here we got A1 by A2. As we know that A1 equals to pi by 4 d1 square and A2 is pi by 4 d2 square. So pi by 4 gets cancelled. D1 square by divided by d2 square will get 3.57. Hence, d1 by d2 is square root of 3.57. So it is 1.89. So d1 is 1.89 times diameter of d2. How to find out the work done and the ratio of the area or the ratio of diameter in case of steady flow energy equation. Similarly, one more problem, just a simple problem. In a gas turbine, the gas enters at the rate of 5 kilogram per second with a velocity of 50 meter per second and enthalpy of 900 kilojoules per kg. It is a gas turbine problem. M mass flow rate is 5 kg per second. The V1 is 50 meter per second. Enthalpy is 900 kilojoules per kg and leaves the turbine with a velocity of 150 meter per second. That is V2 is 150 meter per second. Enthalpy H2 is 400 kilojoules per second kg. The loss of heat from the gases to the surrounding is 25 kilojoules. Okay. Assume gas constant they are given, Cp is given, and inlet conditions are given. Okay. Determine the power output of the turbine and the diameter of inlet pipe. Okay. So first you have to write the steady flow device, that is a turbine. This is the turbine device, and you have to write the equation, that is W into H1 plus V1 square by 2 plus G Z1 plus dq by t. So you remember this formula, okay, steady flow energy equation, and we have to find out dW by dt is W into H1 minus H2 plus V1 square by 2 minus V2 square by 2 plus dq by t. We are shifting all the terms towards left hand side and we are going to find out dW by dt. So H1 minus H2 V1 square by V2 divided by 2 plus dq by t. So 5 is the mass flow rate, 900 enthalpy is given, 900 minus 400. And one more thing, here 50 meter per second is given. You have to convert in kilo units. That's why 50 into 10 to the power of minus 3 you have to do. Suppose you are not doing 10 to the power of minus 3, it is wrong. So in any problem, be careful in conversion of the units. Minus of 25 into 5. Okay. So why minus means it is a heat rejection, heat losses, heat from the gas to the surroundings. Okay, loss of the heat. Loss of the heat means you have to take minus. Okay, that's why you have to analyze the problem carefully. Whenever loss is there, you have to use minus symbol. Whenever gain is there, you have to use the positive symbol. Okay, after solving this one, we are going to get 2325 kilowatts. Okay, and mass flow rate. So here we are using the ideal gas equation, that is P1 V1 equals to MR T1. MR is nothing but M is nothing but what? Here mass flow rate. Okay, you have to take. So here volume we have to find out volume flow rate. Volume flow rate is nothing but meter cube per second. We have to find out V1, that is 5 kg per second into R is 0.285 given in the problem. Temperature T1 is 300 divided by 100 into 10 to the power of 3. Once again, you have to convert in kilo because they are given in kilo Pascal. You have to convert in Pascal. You get 4.275 meter cube per second. The inlet area is A1 is, we know that mass flow rate is A1 V1 divided by small v1. Using that formula, you have to find out A1, that is area at inlet. Area at inlet is 4.275 divided by 50. Then you have to find out, we know that A1 is pi by 4 d1 square. Okay, so 0.086 equals to pi by 4 d1 square. After simplifying this one, we are getting the diameter at inlet as 0.33 meters. Sometimes they may ask to find out the diameter at outlet. In the same way, you have to find out, but mass flow rate remains same. You have to write it as pi by 4 d2 square. Okay, so using that one, you can find out the area at outlet. Try to solve some more problems on this one steady flow energy equation. Okay, so you have to do more number of the problems in first law of thermodynamics and the steady flow energy equation. Try to solve the problems. Okay, you refer any textbook. Okay, so there will be a lot of numerical problems will be there. Okay, go through, try to solve it. Okay, and get the answer. Okay, then compare the answer. For example, if it is a compressor, you will get the negative work done. For turbine, you get the positive work done. Like that, you have to analyze your answer also. Okay, and also see in the problem we analyze that v1 is 5 meter per second and v2 is 7 meter per second, means that the velocity is almost same. Okay, so that's why we are neglecting those terms in the equation. Like that, not only this one analyzing problem, you have to analyze the values also and magnitude also and the conversion of units also, most important. I'll do some more problems in the tomorrow class. Okay. So those who have not done, not entered USN, please enter USN in the chat box without fail. I'll stop the recording now.